Okay. Welcome, everyone. Today is our first session of a new series that we have started at PyWhy. We are calling it Causality in Practice. And this is based on a lot of feedback and requests that we were getting from the community, that people wanted more exposure to not just the tools that we are building, but also the fundamentals of causality behind them. Uh, and so we thought, why not maybe have a talk series where we'll focus on some of our tools in the PyWhy ecosystem, but also some lectures will be just on interesting advances in causality or even tutorials on different parts of causal inference. So we'll try to do a mixed bag. And so for today, I'm very pleased to have Emre Kiciman, my longtime collaborator on DoWhy and also many other causality projects with us. Uh, so we'll start with a very exciting topic, which is large language models and what it means for causal inference. Right? Now, I know many of you might still be thinking, what do these two things have to do with each other? But that's exactly what Emre will try to enlighten us about. Uh, so without further ado, I'll just transfer to Emre. So a couple of ground rules for this series. We will have these on Teams calls and they will be recorded. For the first 45 minutes or so, we expect the speaker will give their presentation. So we'll appreciate if the audience can mute their mic. If you have questions, you can just put them in the chat. I mean, there's a chat window on Teams. You can just put those questions. And after the speaker has finished, we'll have a live session where you can unmute your mic and ask them questions. Okay, with that, over to you, Emre.
Thanks very much, Amit, and thanks everyone for attending today. I think this first session might be a little bit more casual than a 45-minute straight through presentation. So let's just see how it goes. Feel free to raise your hand or type in a chat, and I'll try to actually get to your questions in line, or let you know that I'll get to it in a little bit. So yes, this talk today is about a new repository in the PyWhy GitHub organization called PyWhy LLM, and this is going to be an informal, I couldn't help myself, I said casual, introduction to the library. And first, I want to give a brief motivation for the purpose of this library. It's really about integrating large language models in a way that helps with what I know many of you also think is a fundamental challenge in applying causal analyses in practice, and that is the question of where domain knowledge comes from. And this is based on a paper that Robert, Amit, Chen Hao, and myself put onto GitHub archive last spring, looking at what large language models could do for causal reasoning. I think we have some very exciting results there, and I can open up a separate slide deck to get into some of those results if it's interesting for the audience. But really, so just to motivate the purpose of this project, I want to highlight one of the major challenges in getting reliable observational studies in practice, and that is, I think, illustrated by best is illustrated by example. So, for example, if we look at some of the most prominent examples of observational studies failing, we see things like people coming to conclusions that say that, for example, maybe night lights cause myopia in young children, or vitamin C and E reduces heart disease. And these are things that seem to be true when you look at observational data, or at least when that seems to be true when you look at observational data, but actually turn out not to be replicable in follow-on studies, even randomized control trials. So just to give a little background on this, so in the in 1999, there was a big headline in a Nature article that said that families who had night lights in their halls, so there was always some light source somewhere, even in the middle of the night, that children growing up in this environment were more likely to get myopia. And this was actually pretty widely discussed. It even made it onto, the nightly news headlines, and people were quite concerned for a while. But follow-on studies weren't able to reproduce this analysis result, and it turned out that the authors had missed a common confound, and that is that it turns out that parents who had myopia were more likely to use nightlights in their home. And of course, then this opens up the uh, a influence to occur between the genetic predisposition of the parents and the children to have myopia. And this meant that the entire effect that was being seen here was actually not due to the nightlights themselves, but due to a common confound. There have been many claims over the years that vitamins reduce heart disease, have other health benefits, and these have failed RCT replications, mostly because people believe that there's been multiple confounds that were unaccounted for, in particular, like socioeconomic status. Meant that confounded people's likelihood of taking these vitamins with other healthy behaviors like exercise or ability to go to a doctor early, for example. And in fact, survey studies of claims, in particular, the Young and Carr I'm citing is from health and medical related claims, find that none of the observational studies in this survey were reproduced. In fact, several of them were contradicted by RCTs. And so this does not bode well, and most of these were because of failure to account for common confounds or other kind of other biases in their data. If you're interested in more of these, I recommend checking out Ronnie Kohavi's Refuted Causal Claims site, and he's very helpfully collected these claims, and they're fascinating to go through and study. Now, many of these studies, the studies I'm citing here are, a decade or two old, but these similar problems actually continue today. For example, at the beginning of the pandemic, many labs around the world started to build machine learned classifiers that took a chest scan of a patient and then tried to identify whether the patient had COVID or not, as a diagnostic test, right? And follow-on studies over the next year or two found that of the hundreds of chest scan classifiers that were produced, none of them was actually fit for use in practice. And this was because the majority of them, it was because the underlying training data had false correlations embedded in the data sets. So, for example, one classifier was built from data taken in a hospital that had a policy of allowing patients to to decide themselves whether they would sit or lie down for the chest scan. And the sicker patients, in this case, the ones who actually had COVID, were the ones who were likely to lie down. Now, sitting versus lying down has leaves other markers in the chest scan. And so the COVID classifier in this case ended up being a classifier of whether the chest scan was taken sitting down or sitting up or lying down, which did not transfer well when going to other hospitals, of course. In the second case, just to give another example, the data used to train the COVID classifier was taken from a data set where all of the negative chest scans, so all the people who did not have COVID, were actually pediatric patients. At the time, children were getting COVID at lower rates. And so as a result, this classifier ended up actually simply looking for signs that the chest scan was of a pediatric patient, a child. And so that meant that, again, it was not actually looking for the real signs of COVID. So again, this is examples of some structural domain knowledge influencing or biasing a data set that was being analyzed. Previously we were looking at observational studies, causal analyses, and here we're looking at um, we're trying to build a robust prediction, but in both cases, not capturing the domain knowledge about the data generating process meant that these analyses did not do what they were intended to do. And so PyWhy LLM is intended to bring large language model support to reduce the burden on a human domain expert to identify all of those potential challenges. So we see that there's two fundamental challenges for causal inference that require human um, input. We'll be focused on the first one, on the assumptions necessary for a causal argument, e.g., where does the causal graph come from? But in general, it's LLM. It's the we see that LLMs are good at exactly these tasks that need human input. They've been, especially the largest of the large language models, have been trained on large amounts of text from across the internet, and they have embedded in them the domain knowledge about the relationships between many of the factors that we care about. Um, Sorry. Just a second. Okay, I thought a slide was missing. Yes. So um, what PyWhy LLM does is it builds in simple protocols for the tasks that we would want LLMs to help with at each stage of causal analysis. So during measurement and modeling, we are implementing functions that allow the LLM to help us build the initial model of a problem. So what are the potential causal relationships given a data set, given a particular treatment outcome question, and what are potential latent confounders that we haven't thought about yet that aren't in our data set, question support such as that. Normally, this is during this step, a analyst or data scientist would be going out to talk with domain experts, sometimes many domain experts, if your problem is crossing multiple areas of expertise, and then go back and forth and until you're satisfied that you have captured all the relevant domain knowledge. During identification, we can ask different questions. We can ask directly whether there are potential instrumental variables, for example. And during validation, we can ask whether there are any negative controls, whether there is any critique of a causal graph that, say, a human or a domain expert has generated on their own. And this allows us to integrate large language model support for the areas where we required a human to really lean into the process previously on their own. There's one step here that I skipped over. That's effect estimation. During effect estimation, we are during this entire process, we are actually seeing LLMs as an augment or complement to the current algorithms we have. So, for example, if a causal algorithm, if a large language model suggests a particular instrumental variable and we have access to the causal graph, we can validate that is an instrumental variable, a valid instrumental variable, by testing the necessary assumptions. We can, and during effect estimation, I think, should be using all the existing data analysis algorithms that we have, the algorithms that are implemented in EconML, for example. And then we can, and so PyWhy LLM doesn't do very much during effect estimation. We think one interesting task is to actually generate the code necessary for running EconML over a specific data set. Oh, and I shouldn't leave out that during measurement and modeling, this stage where we're asking an LLM to support us with domain knowledge, there's an opportunity here to bring in an integration of the LLM with causal discovery algorithms as well. So, um, so I think this is going to be a case where we see the LLM and existing algorithms working together, working better together. So PyWhy LLM is a shared library for defining and implementing these tasks across each of those stages. It is designed for experimentation at this stage, so we have a lightweight protocol interface, and the idea is that we want to have room for both simple and complex implementations to live side by side. I'll do a brief walkthrough of some of the simple implementations of these tasks that we've defined initially. And I'll also point out some of the places where I think we need more complex implementations as well. So I'm going to stop sharing my slides at this point and then move over into a Visual Studio Code window. Are there any questions that people had before I move into the code? All right. Okay, so I'm sharing my screen right now with a Visual Studio Code window open, looking at PyWhy LLM. My local copy here is maybe is going to be one commit or so ahead of what's on GitHub right now, in case you're looking at that. But move my screen over so I'm not looking to the side so much. So what we have here is in PyWhy LLM is a folder called suggestors, and inside suggestors we have protocols defined, and we have one protocol for each of the four steps here. So as I said, for example, the estimator only has a function call defined for suggesting code. But some of the others, for example, modeling, are a little more interesting. When we're in this first modeling stage, we can ask the LLM to ask the library to suggest pairwise relationships. So given two variables, which one causes which? We can ask it, we can give it a set of variables, and it will give us back a graph. And then we can give it a set of variables that we've already considered, and then a specific treatment outcome pair, and then ask the LLM to suggest confounders. We have similar interfaces for identifiers. You know, we can ask it to directly suggest a backdoor or a front door path or an IV as well. Now, each of these functions is intended to tie in directly into the rest of the PyWhy ecosystem. So for example, when we get back a variable relationship, there's a to-do here that we need to make sure that this returns a network X graph that plugs in directly into do Y, or is directly usable by causal learn, for example. Let's see. Other let's see, I'm going to go into, okay, so now that we've seen what identification, modeling and identification look like, estimation is just code, then validation, this one's a bit messier, but there's two here that we've implemented more complex versions of, critiquing the graph and suggesting negative controls. Latent confounders is one I think that we're going to integrate back into either critiquing the graph or into, or that already exists in the modeling stage. See. So what does the using this look like? I'll go into tutorials. There we go. So let me reset my notebook and I'll step through. So the first thing I'll do is import guidance and yeah.
Just a comment, you may want to increase the font. I think it may help people.
Oh, thank you very much for that comment. You'll have to bear with me a second. I don't usually increase the font on my screen, so I'm Oh, that did it. Great. The keyboard shortcut worked where my menu is failed. Okay, great. All right. So the first implementation that we have for these protocols relies on guidance. And unfortunately, the guidance library, if you're not familiar with it, it's a really well-designed library, but it is currently in a bit of a unstable state while the maintainers are focusing their efforts on a branch. That branch should be, I think, merged back into main. I think I've heard the maintainers say over the next like week or so. So maybe two. In the meanwhile, we're in this unfortunate state where I have a little comment here that says this requires guidance with the main branch of guidance with the specific PR to be merged in. But then okay. But we'll resolve that as soon as they merge their branch back into main. So what I'm doing now is just loading these kind of first libraries, setting up my API, and then what we'll do is first we'll test out, the functionality in this simple model suggester. With this implements that protocol that we just saw. Okay, so the first thing I want to show here is what it looks like to test a pairwise relationship. So in this case, I'm going to use the modeler suggest pairwise relationship function and pass in two variables, ice cream sales and temperature, and ask if one causes the other. So you'll see that the result here is that we see the conversation going on with the chatbot, where it considers each of three multiple choice options. Ice cream sales cause temperature, temperature causes ice cream sales, or neither ice cream sales nor temperature cause each other. And then the AI then thinks through each of these, through each of these options, and then decides what its final answer is. And then to make it easy for parsing, we ask it again, now what's your final answer? And we force it to give a parsable result. It can only answer A, B, or C at this point. That then gets parsed back into a structure that's a little bit easier to use. It's the variable that's causing the next variable in this order, and then the description for future reference if useful. We can print that out here. So we can say that if the result is not none, so we did get an answer back, then result 0 causes result 1. Otherwise, it says neither causes the other. So I'll go ahead and actually click through here and see that ice cream sales seems to, see that the answer is B. That is that the temperature causes ice cream sales, but not the other way around. And if we come back up and maybe change this around a little bit, let's say that we're going to ask now about the relationship between ice cream sales and shark attacks. We'll push play on that. And what's your final answer? This time it says the final answer is C. Neither ice cream sales nor shark attacks cause each other. And if we want to access this programmatically, we see that the answer here is none and none. And so it says neither causes the other. Now, we can have some fun playing around with different relationships, but I'll just quickly give a peek at what this simple model suggester is doing behind the scenes. And here what we have is the implementation of that function. It is setting up a guidance prompt where we are in a chat conversation. We first tell the LLM that it's a helpful assistant for causal reasoning, then ask it which cause and effect relationship is more likely, and fill in these variable names here, and ask it to then think about each option and then provide a final answer. The chatbot has the ability to now go into its description of its reasoning, where it now analyzes A, B, and C, as we saw earlier. And then we'll ask it again what its final answer is. and will force it to select an answer between A, B, or C. Our Python code then runs this guidance program and pulls out the variables, both the description with the long text as well as the final answer, and then formats it into this array for returning. And that's it for this particular function. Now, there's um, several now opportunities to extend this function with more more functionality, and I'll point out a couple of them. One is that in some cases we might want to add a deeper description of each of these variable names. So we might not want to just use a short name for this variable, but we might instead want to add in a longer description of where this data came from, how it was collected, etc. So that's one thing we might want to do. A second is we might want to tell the assistant that not only the LLM that not only is it an assistant for causal reasoning, but that it's also maybe a domain expert in a particular field. We find that this type of extra instruction can sometimes make a difference in the quality of the LLM's results. And finally, there's also a room to change the way that the LLM thinks about its final answers to correct for simple kinds of errors. So I'm going to actually pull up a different slide here and drag it into view. So for example, in our previous work, we found that one of the common errors in the LLM's answers was that it would sometimes misinterpret the concepts behind the variable names that we were asking about. So, for example, when we asked GPT-3.5 about the relationship between ozone concentration and radiation, the benchmark that we were grounding our work in said that the right answer was that radiation causes ozone levels. But the LLM told us that ozone actually causes radiation. And the issue was that the benchmark data set was asking about ozone concentrations at ground level with the radiation being discussed being radon, whereas the LLM was asking about ozone in the atmosphere and the stratosphere and its effect on UV radiation. And so one thing that we can do is actually ask the LLM whether there are any ambiguities that would make it change its answer, and that would be another round of chat that we could implement in this prompt program here. And if so, we have the option of going back to the user with a question or returning both results and asking the user to pick which one is most appropriate. This type of ambiguity actually can happen fairly easily. So, for example, a couple of weeks ago in an analysis I was running, I was asking about the columns of data that would appear in a medical health electronic health records, and the LLM told me that then there was a column called sex, meaning gender of the patient, and then also, or biological sex of the patient, and then also a column on whether the patient had a prior history of heart attacks. The name of the column, though, was simply the first column was simply sex, and the LLM misinterpreted it as being a Boolean indicator of degree of sexual activity, and went into a long kind of description about how sexual activity could cause cardiovascular strain, but that it was unlikely to be doing so. Um, and that is, was one of those cases where the LLM was misinterpreting the column name, and we'd want to fix it. All right, I think we've gone through quite a bit. I have a couple of more of these snippets, but again, this is a good time to pause and answer any questions. All right,
Hi,
I'll move
Emre.
on. Oh, yes.
Yeah. I was doing something similar with finance, time series, and there was one in particular about unemployment and unemployment rate and interest rates. And it's kind of interesting. Like I was using a similar prompt, and the result I got back was that they cause each other, which was kind of interesting because obviously I guess it depends on the economic theory. Different scientists have different, different economies and different ideas. But I think maybe we should also include that option to see if they are co-occurring, because sometimes maybe it's true, like one causes each other in a closed loop fashion, or sometimes it could be that there are different opinions about a specific theory. So yeah, that was kind of interesting. I got that result. It was, most people assumes that, interest rate and GDP influence unemployment, no, vice versa. But I just thought it's kind of interesting thing I got from that.
That's a great point. That's in longitudinal settings, especially the potential for feedback loops is real, and adding that into the model would be great. I think we don't have a great way of representing it in the underlying network hex
In
graph that we'd
the
want to
DAG,
return until we have that broader kind of time series support, I think. But yes, definitely something that would be useful to put in here. Mm-hmm. Yeah,
Right.
and there are even
Yeah.
in the non-longitudinal data set scenario, it's something that we could find a way to return to the user and highlight, mitigations that they might take. So, for example, being careful about at what point in time their measurements were taken relative to one another, and that might imply that they prefer one or the other representation. So that type of advice to the user would be great.
Great. And the other, I'm not sure about this library by this generator. So I can see. Usually I've seen people when they do prompt for OpenAI, the interface, they have messages with the one that you were showing your template. It looks like a single string, but usually, what I've seen so far, they pass them as an array of prompt messages. Yeah, so this one, it's like I don't know if it makes any difference to have these as free messages that you pass to OpenAI. One is system, user, I guess is user again. But yeah, I'm just thinking, does it do anything in the background, this library, or does it just replace these variables as a string and that's it? Or is it like clever and chunks them into, I don't know, sentences or anything like that?
Oh, yes. This library, it's more useful when you're working with local large language models, like Llama or something. It is able to more tightly integrate into the decoding that's happening with the large language model. But even with OpenAI, it does provide some help. And I'll point at the one thing that it does. Well, first of all, yes, it does replace these variables. And it is aware of this chat interface. So it'll provide this whole thing as the chat prompt, and it'll stop at this generation mark here. And it'll generate this text and then put it into the description variable that it returns. Then the LLM will return here, and then then it'll send in another request with this user message being sent in. At this point here, where it's selecting an answer for it is able to actually looks at these options and sets the logit biases that it provides to the OpenAI API. It sets
Okay.
the logit biases so that even the web API can only return either A, B, or C. So it asks for one character back, one token back, and it has to be one of these. When you're working with the local large language model, this whole interface becomes much broader. You can put it in the, even potentially in the middle of a text generation that you're doing, etc. If it's not a chat model, this becomes much more powerful. But yeah, with the web API, it's a little bit limited, but it's still kind of a nice way to kind of succinctly write out a multi-stage interaction like this.
Yeah.
Yeah, and this is really great for having to, for parsing. Like I just literally just read off his answer as you see down here, and I'm guaranteed that it's going to be A, B, or C.
Yeah, yeah, because in OpenAI they usually use functions with, you have to provide these JSON templates or this kind of, basically you have to write a parser for that, and sometimes it's tricky, like it doesn't get the schema right, and you have junk in the responses. So this seems to be more neat. Yeah, you have more control on the outcome.
Definitely. Now, I do want to emphasize that the protocol itself here, where we are, providing this makes no mention of guidance. So, if there's interest in using LangChain or LLMQL or any other approach, really, that can be a separate implementation. The main thing here is that we want to provide some direction about what tasks we think are useful to implement. And if you're implementing that task, then try to support this
this interface.
This interface.
Protocol.
If you need to add more things on, add more variables on, especially as optional, etc. But
Nice. Yeah, makes sense.
Yeah, some structure, but I think we're still at very much an experimentation stage here, so it's intended to be a very lightweight structure. Yeah. Great. Okay, so if we want to build a graph among multiple variables, we simply, list out the variables that we have. We call the suggest relationships function over that list of variables, and then the LLM will go through and do all of its thinking, and we'll get back an array or set of these that tells us that temperature causes ice cream sales and that ice cream sales cause cavities, and those are the two edges between those three variables that we just saw: temperature, ice cream sales, and cavities. And this is now where we'd want to convert this into a network X graph, right? So that we can feed it directly into the rest of the PyWhy tools. I'll spend one more second on latent confounders. And so here again, we have a set of variables that we've considered, and we want to suggest confounders that maybe we haven't thought about. So we'll ask the library to tell us, okay, we're looking at estimating the effect of ice cream sales on shark attacks. What are some confounders that we need to be considering? And we'll get this nice result back. That's so things that you might. Okay, things that you might need to consider are beach attendance, season of the year, water temperature, public holidays, availability of ice cream vendors, shark population, swimming conditions, tourist season, etc. These are not grounded in any data set we gave it because we're telling it to give us latent confounders, things that we don't necessarily have measured yet. But this is a nice list. We can repeat the task for analyzing the result between the relationship between vitamin C and cardiovascular health. In this case, we gave it no prior factors we've considered. So this is a very open-ended, and it gives us a list: dietary habits, physical activity levels, smoking status, alcohol consumption, etc. Long list of things to consider. And actually, I didn't point this out earlier, but we do still have the description where it give some explanation why physical activity level, for example, may be a confounder. Yep. So a very nice brainstorming tool there. Similarly now, we can repeat this same type of prompting for suggesting, directly suggesting identification approaches. So while we can generate the DAG and then run like a backdoor analysis or on the graph to identify an approach to estimating a particular causal effect we want to estimate, the library, there are scenarios where maybe there's some domain expertise that allows us to get straight at a particular identification approach without having to generate the full graph. And that can be useful if that graph is particularly complex. So in this case, for example, oops. Oh, I have to do that. Okay. So in this case, for example, I'm saying that we have a number of variables that we've measured, maybe cigarette taxes, something about the weather. I'm purposefully putting in some irrelevant things like car sales and property taxes. And then say I want to identify the effect of smoking on birth weight. And now when I ask this question, it says, well, cigarette taxes would be a good, from that list, cigarette taxes would be a good instrumental variable for identifying the effect of smoking on birth weight, which is nice. We can do the same thing for backdoor variables in different scenarios. Front door as well. Front door, I'm not sure this one is working. I'm not sure I believe this result as much as I say like the way that the cigarette taxes one came out. And so this takes us through the first couple of protocols, modeling and identification. We don't yet have an implementation for estimation, and we don't have an implementation for a simple implementation of validation. I will point out that we do have complex versions. So I was showing you the simple the simple model suggester and the simple identification suggester code, but we do have, for example, a model suggester, which provides a lot of the functionality that I mentioned. For example, allowing you to list what expertise the LLM has, and allowing you to even see. In the factors list, I believe the factors list also allows column descriptions and things like that to occur. This version, I think at the moment in the GitHub repository, there are a couple of errors that I'm getting when I run the complex version. So it does need a pass, a debugging pass to go through it. But at this point, I think I'll, looking at the time, open it up for kind of wrap up questions and things like that. One thing I do want to emphasize is that, I think we'd all be very happy to accept any changes or suggestions. Please feel free to start taking a look, but do be warned that the library, as I mentioned, is not like, is still very much in an experimental state. And so it is not something that is stable at the moment. Thanks.
Thank you, Emre. And in fact, I'll say, in a sense, this is deliberate that we are presenting this library so early on in its development. Mm-hmm. It is to see what feedback you can give us. And also, if you want to contribute and sort of shape this library, I think that's welcome as well. We would love as many contributions as possible. This is a very new topic. I think this is very tricky to sort of set up the right pipelines. So any feedback here would be very useful.
Yep, 100%.
Is there any plan to implement something I mentioned in the forum, an agent? Well, that's LangChain, so that there are agents. There is one for pandas, for example, where you you create this zero shot agent where you pass a pandas data frame as an argument, and then you can ask questions edge of this column, and it knows about entities and that kind of stuff. But I'm thinking it would also be nice to have an agent where you pass the causal model object, and you can ask, give me the estimate of this column, which is a treatment to this effect, which is this other column, and maybe also suggest what methods you should apply, what you shouldn't. I think that's something I can start to write the base code, because I've been looking into LangChain for a while now, and then the question is now, how do we merge these two? Because obviously inside that agent you will also have to do some prompting, within a kind of similar interface. But yeah, just to get some ideas. I'm not sure how many people use LangChain, so that could be a barrier.
I think that'd be a great thing to put into here. I mean, not our initial structure is around these suggesters, is what we're calling them, but an assistant that helps with more of that end-to-end process, I think, would be great. I also don't know how many people use LangChain versus other tools like the Baby AGI, AutoGen, or others. But I don't think that should stop us from experimenting with the general approach, right? And then my kind of take is that we can start with LangChain and we can switch to something else if right in this fast-moving field.
Okay, I'll put something together, like just a proof of concept, and then we can see how can we kind of improve that, or use one library into the other one, which I think should be doable as well.
Yes, yeah, that'd be great.
Cool. Thanks.
Thank you. Cool. Well, if there aren't any other questions right now, feel free to reach out on the Git, especially on the GitHub site, filing issues or discussions, or on our Discord with questions as well. I know I'll be monitoring that all as much as I can. And on the in terms of the code that you just saw, I expect it to be pushed as a PR to the website, to the GitHub sometime early today. So you should see it there soon.
Awesome. Thanks a lot, Emre, for this talk. We look forward to future developments with PyWhy LLM and also integrating them with our existing PyWhy libraries much more strongly. So we are always available. So Emre will be available on Discord as well. So if you have more questions or would like to reach out, you can reach out to him on the PyWhy Discord channel. Okay, with that, thank you, everyone. And we'll see you in 2 weeks' time. So this will be a bi-weekly talk series, and the speakers will be announced on Discord. Okay.
Thanks,
Thank you,
everyone.
everyone. Bye-bye.
Thanks.